In this video, we're going to finish up Chapter 6. 6.5 is where we're going to look at the graphs of y equal tangent x, y equal cotangent x, y equals secant x, and y equal cosecant x. Of course, we've already looked at the graphs of y equals sine x and y equal cosine x. That was in the last section. So let's take a look at y equal tangent x. I've already got some triangles set up here that I'm going to be using along with the unit circle for the major angles. If I let x be 0, then remember, tangent of an angle is where you take y over x. So y is 0, x is 1. 0 over 1 is 0. Okay, so here's 0, 0 on the graph. If x is pi over 6, I've got my 30, 60, 90 triangle set up here. This would be a 30-degree angle. And tangent of an angle is where you take opposite over adjacent. 1 over root 3. 1 over root 3, it would be roughly about 0.6 if you go nearest one digit on that. So pi over 6, roughly 0.6, that'd be about right here, I guess. And then if x is negative pi over 6, I've got a 30, 60, 90 right triangle, but it's in quadrant 4. The opposite side is negative 1. The adjacent side is still root 3. Negative 1 over root 3 would be my output. Okay, so negative pi over 6, negative 0.6 would be about right there. If I let x be pi over 4, here's my 45, 45, 90 right triangle. Opposite over adjacent, both those numbers are 1. 1 over 1 is 1. And so pi over 4 is right between 0 and pi over 2. You're going to be at a height of 1 there. If x is negative pi over 4, here's a 45, 45, 90 right triangle, but it's in quadrant 4. The opposite side is negative 1. Adjacent side is 1. Negative 1 over 1 is negative 1. So here's negative pi over 4, negative 1. Okay, if I let x be pi over 3 next, then here's a 60-degree angle. I've got a 30, 60, 90 right triangle. Opposite over adjacent. Root 3 over 1 is root 3. Root 3 is roughly about 1.7 if you were to look at the decimal form of that. So at pi over 3, it'd come up to a height of about 1.7. That'd be about right here if you were to plot that point. If x is negative pi over 3, that triangle would be flipped into quadrant 4 here. The opposite side is negative root 3. Opposite over adjacent, negative root 3 over 1 is negative root 3. Okay. If x is pi over 2, then there'd be a problem. I can't divide by 0 here, so I'm going to have undefined. Same thing if x is negative pi over 2, that's going to be on this axis. I'll be dividing by 0, which is not allowed, so I'm going to also have something that is undefined. Okay, now because we're not having a definitive number come out of the calculation, we're going to have a boundary on the graph. Two boundaries at x equal pi over 2 and x equal negative pi over 2. Of course, the curve is going to be approaching those boundaries, passing through the points that we've already got plotted there. Now, the tangent function is a periodic function. All 6 trig functions are periodic, right? But the tangent and cotangent functions have a period of pi radians, not 2 pi radians. Now, if you look at the distance from negative pi over 2 to pi over 2, that would be a distance of pi radians. So what I see here on that interval would repeat infinitely often. Okay, so I've got like 0, 0 is on the graph, pi 0 would be on the graph. Here is pi over 4, 1. Okay, 5 pi over 4, 1 would be on this section. Here's negative pi over 4, negative 1. If you go pi units to the right, 3 pi over 4, negative 1 would also be on the graph. Okay, and so I've basically just drawn this curve infinitely often here. This section infinitely often. There's going to be infinitely many asymptotes on this graph. And just some basic properties of the tangent function. The domain would be all real numbers except for the values that you're going to produce asymptotes. Okay, so x cannot be k times pi over 2, where k is an odd integer. So like pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, etc. You're going to have asymptotes at that spot, at those spots. So x those x values would not be in the domain. The range is all real numbers. We can see that the curve is going to cover the entire y-axis there. F is an odd function. We learned that in the last section, that the tangent function is an odd function, so the curve is going to be symmetric to the origin. And let's see, the intercepts, there's going to be infinitely many intercepts on this graph. 0, 0, pi 0, 2 pi 0, 3 pi 0, I've got those listed. Negative pi 0, negative 2 pi 0, etc. Okay. And of course, we can use what we know about transformations to produce more graphs. Okay, so like if I want to graph y equal 2 tangent x, I would take the tangent curve and multiply all the y values by 2, and that would produce a vertical stretch by a factor of 2. So I've selected a couple of points here that were on the original graph. Pi over 4, 1 is 1 point. Okay, if you multiply the y value by 2, that'll put at that point at pi over 4, 2. Pi over 3, root 3, that was another point that I had plotted earlier. Multiply the y value by 2, and so that point is now going to be at pi over 3, 2 root 3. Pi 0 is just going to stay right at pi 0 since your 0 times anything is 0. Okay. The asymptotes are also going to stay the same, by the way, on that new graph. Here's another example. So if you have y equal negative tangent of x plus pi over 4, the negative means that you'll be reflecting about the x-axis, and then the plus pi over 4 means that you'll have a shift to the left of pi over 4 radians. So if you imagine doing those two transformations, the graph is going to be different. Okay, here's a couple of points that are going to be going to different spots. We just look at maybe one of these here. Pi over 4, 1 was on the original graph. When you reflect that about x, that'll put you at pi over 4, negative 1. And then you're going to be shifting to the, which way we shift in here? We're going to the left, pi over 4 units, so that'll put us at 0, negative 1 then on the new graph. Okay, and here's where a couple of other points are going to be going. The asymptotes are going to shift to the left also by pi over 4 radians. Okay, and then I've got y equal cotangent x. How I'm getting that quickly is I know that the cotangent function is the reciprocal of the tangent function. Now here's the same table that I have already used previously in getting the tangent function, and I've got the output values, and I'm just going to look at the reciprocals. Okay, the reciprocal of 0 would be something that's undefined since I can't divide by 0. I'll have a vertical asymptote at x equals 0. The reciprocal of 1 over root 3 is root 3. Okay, so pi over 6 root 3 would be about right here. The reciprocal of negative 1 over root 3 would be negative root 3. Okay, so that point, negative pi over 6 negative root 3 would be about right here. The reciprocal of 1 is 1, so pi over 4, 1 is on the graph. The reciprocal of negative 1 is also negative 1, so here's negative pi over 4, negative 1 on the graph. Okay. The reciprocal of something that would be undefined would be 0, so pi over 2 is 0 would be on the graph. Also, negative pi over 2, 0 is on the graph. Now, I've looked at, so far, what the curve would be if I'm between negative pi over 2 and pi over 2. Okay, but the cotangent function is periodic, where the periodic factor is pi radians. So if I'm going from negative pi over 2 to pi over 2, that would be a distance of pi radians, and I know that's going to repeat infinitely often. Okay, so this little section here, let's see, if I where are we at? If we this section here, if I slide this to the left, pi radians, that'll be producing the rest of this curve in this section. This part here that I've already got drawn from my table, if I slide that to the right, pi radians, that'll be producing the rest of this curve here in this section. And of course, I'm repeating infinitely often what I see from 0 to pi. Okay. There's going to be infinitely many asymptotes on the graph of the cotangent curve, just like there were infinitely many asymptotes on the graph of the tangent curve. If we were to look at the graph of y equal cosecant x, just to show you what I'm doing there, so I've already got the graph of y equals sine x drawn. That was what I did in section 6.4 there, and you guys already have this already, but I just wanted to point out that I'm using the same table that I was using, earlier when we did this problem. You can see those values already there. And of course, the cosecant function is the reciprocal of the sine function. So I'm just simply flipping the numerator and denominator to get these output values for the cosecant function. There's going to be an asymptote at x equals 0, also at x equal pi, also at x equal 2 pi. Okay, and then looks like pi over 6, 2 is on the graph, pi over 2, 1 is on the graph. You can see some of these other points that I've got plotted. Now, in this table, I've essentially graphed what would be between 0 and 2 pi. The sine function is periodic, where the periodic factor is 2 pi radians. And so what I see here from 0 to 2 pi, again, is going to repeat infinitely often. So I can slide this over and, to the left or the right and be able to get the rest of the graph. There's going to be infinitely many asymptotes on this graph. There's going to be infinitely many hills and valleys. We can see that on this graph. And lastly, for if you have y equals secant x, so we have already drawn the graph of y equal cosine x, and that was in the last video, the last section. Here's, again, just I'm using the same table that was there from before, and you can see the values that we've already got there. And I'm just simply taking the reciprocals of those numbers. Okay, so I can see, like so here'd be 0, 1 on the graph of y equals secant x, pi over 3, 2, that'd be about right here, I guess, about right there. At pi over 2, you're going to have something that's undefined. Okay, so there'd be an asymptote there at x equal pi over 2. Also at x equal 3 pi over 2, there's going to be an asymptote. Now, in this table, I would have been able to draw what you see here on the interval 0 to 2 pi. And again, the cosine function is a periodic function where the period is 2 pi radians, so therefore the secant function is also going to have the same periodic factor of 2 pi radians. So what I see on the interval 0 to 2 pi is going to repeat infinitely often, and I can be able to get the rest of this curve then. Okay, now notice some similarities with y equals secant x and y equal cosecant x, also y equal cotangent x and y equal tangent x. Sorry, I'm moving sheets around here. There are some similarities with how those curves look. Okay, now just like there's the similarities with the sine curve and the cosine curve. Okay, now it's a good idea to know the graphs of these 6 functions. Okay, we will use them. They are important. I would actually have those memorized going into calculus, okay, because you will be using them. You'll be doing lots of things with graphing, lots of things with trig calculations and their graphs. So to me, that's just a good thing to have memorized at that point. All right, we're now done with chapter 6. Here's the homework in section 6.5. Be sure to look at the problems that are on page 429 for me.